Okay, everyone, I think we might be. Okay, everyone, I think we might be. Okay. Let me just make sure that everything is muted and we can start. Sorry about the delay. I am going to try and find my find the moderation view so I can get access to the chat, and then we are going to go ahead with types and how computers think about the world. So today's class is a little bit about like learning how to cook. And when you learn how to cook, you don't start by making a very complex dish. You start by learning the basics, like what type of vegetables go well together, how do you cut things, should you use a skillet or a saucepan, or how should the oven be? So what we're going to do is go through these things that are very basic and that might sound like they don't have a lot of relevance to what is actually going to be happening when we do the process of modeling biological systems. That being said, this is very important because it's going to make the next steps of this class a lot more formalized, and we know what is going to happen, and we understand why we are working in a specific way. I'm still trying to log in onto another window so I can get access to the chat and see what you have to say. And that should be done very soon. Okay, check that. Past login. Good. And I need my security code. Okay. So, yes, I am live. I would like to see my chat, please. My channel. Chat. Cool. Okay. So if you type something in the chat, I should be able to see it, and I will address that. So the big question we're going to try and answer today is, how do computers think about values? And I have put 3 very important keywords in the title of this module that are variable, values, and types. So what we do when we are programming, especially for science, is that we are manipulating values. And an example of the manipulation of a value is 2 plus 2. And if you do 2 plus 2, that is manipulating 2 values. One is 2, the other happens to also be 2, and the manipulation is an addition, and that gives you 4. So 2 is a value, and if we want to give a name to this value, we can turn it into a variable. And so when we write 2 equals 2, we are naming something. So instead of saying 2, we can refer to this value by its name, and its name is a variable. So that's a very important principle to have in mind at all time. When we're talking about a variable, we are talking about the name of something, and that something is a value. So that's sort of a shortcut. If you imagine that you have an array of number, you have a vector with 1,000 values, instead of explicitly saying, hey, I have this 1,000 values in this vector, you just give it a name, and you use this name to refer to what is to what the values are. So that's sort of the first two definitions that we're going to introduce in this class. A variable is the name of a value. Now, what is a type? So let me give you a quick example. So if we ask Julia, our programming language, what is the type of 2, it's going to say int64. There's a lot of information in here, and we can sort of split it into 2 parts. The first part is that is an integer. It's a number that has no decimals, and it is represented using 64 bits. So that means there's a lot of room. It can be a very big number. We can have different types of integers. Some are smaller, some are medium sized, some are really big, some have signs, some don't. There's a whole variety of ways to think about numbers. Now, one thing that is fairly interesting is that if we ask what the type of 2.0 is, we get a different answer. And the answer that we get this time is it's a float 64. So that is a number which has a floating point number. It has decimals, and it is also represented on 64 bits. Now, the first thing that should pop into your mind at this time is that for us, 2 and 2.0 are exactly the same thing. They refer to the same value. For the computer, that is not true. There is a difference between 2 and 2.0, which is one as decimals and the other as not. This is going to have all sort of consequences in a couple of weeks when we are going to try and make our programs as fast as we can. Everything in Julia, everything has a type. That's very important to keep in mind, even so it's not quite obvious yet. But if we do the type of hello, it's going to be a string of character, and if we do the type of a, it's going to be a character, this sort of things. If we do the type of, let's say, cosine function, it's giving us something that is a little bit strange. It says a type of cos is a type of cos because that's sort of a little tautology like that. And we'll get to what that actually means in a minute. So yes, question from the chat. I don't find the Julia REPL. If you don't find the Julia REPL, let me close this one. There are a couple ways to get it. The first is that you pick any line that you want and you do control and return, and it's going to spin up on its own. Like, assuming that you went through the process that we discussed last week of installing VS Code and the VS Code extension and everything is working. That's solution number one. Solution number two is that you get access to the menu, and the menu is Shift, Control, and P, or it's probably Shift, whatever the Apple key is, and P. And then you type Julia, and there is an option which is called Start REPL. It's also telling you that you could do Alt-J and Alt-O to open it. So if we do, Alt-J, Alt-O, it is going to start the Julia REPL. When you're working in VS Code, as a little aside, whenever you do Alt-J, the thing that comes next is one of the Julia command. So there's a list of the shortcuts that you can get. If you don't want to remember all the shortcuts, it's usually a safe bet that you do Shift Control P to get access to the menu. You type in Julia, and that's going to give you a list of options, one of which is the one you want. Okay, so types. Why are they important? Let's get back to the fact that the type of 2 and the type of 2.0 are not the same thing. It's going to have an immediate consequence for a very simple program that we're going to do here, which is take 2, and we're going to say add 1. So if we do take 2 and add 1, it is going to tell us that it's 3. That's fine. It makes good mathematical sense. If you do 2.0 plus 1.0, it is going to tell us that it is 3.0. That's also good and it makes sense. If we do 2 plus 0 plus 1, for example, or let's do something different. Let's do 2.3 plus 1. The result is 3.3. For us, as human beings, because we have these very complex brains, it's a simple operation because we know that 1 and 2.3 are related concepts that we can merge. One thing that we should be asking ourselves is it as easy for the computer to do this thing? And fortunately, when we are working with Julia, we have a way to sort of peek into how the computer is actually understanding the thing that we are asking it to do. So we are going to use something called a macro, and I won't be going into what macros are until much, much later. Just for the moment, just accept that it's a little incantation, a little spell that we're going to use. And the macro we are going to use is called code underscore LLVM. What that is going to do is take whatever we ask after and tell us what that means in terms of the computer language. So if we do 2 plus 1, the code LLVM macro means, well, when you say 2 plus 1, I understand this block of things here. This block of things here is the expressed in the language that the compiler is talking. The point that is interesting here, the point that is really important, is that it's a single operation. It is creating a variable and then adding two variables, and then the return type is an integer 64. If we do the same thing with 2.0 and 1.0, we have something that is almost exactly the same. We create a new variable, and then this is a result of adding double value. Double is another way of saying it's a floating point value. And then we return this new value. That is a simple operation, and that's a simple series of instructions. What if we do 2.3 plus 1? This one is a little bit more complex because in the previous situation we only had one instruction, which is make an addition. And now we have all of this series of nested things. So what is going on? When we take a floating point value and we add an integer value, the first thing that is happening is this bit here, which is called the promotion. Because what the compiler needs to do is, you gave me two things, like give me an apple and an orange. And they're both fruits, but they're not quite the same fruit, and I need to transform one into the other. And so it's going to go through a series of rules to say, okay, I can take the integer and I can transform it into a floating point value. So I'm going to do that, and that is a series of instructions that I need to do. And then when this is done, only at this line am I going to add this new floating point value I've created to the old floating point value that I add. So it goes like 2.3 plus 1, transform the 1 into 1.0, and then add it to 2.3, and then return the result. This is very important because the more instruction we do, the more instruction we need to get a result, the longer the program will be. In practice, the time difference between all of that is going to be very, very small. So if we do time, let's say 2 plus 3 plus 1.0 is taking, well, okay, that's not a really good example. Let's do it 1,000 times. We're going to do that 1,000 times, and if we do it 1,000 times, I should really... Okay, if we do it 1,000 times, it's taking 0.05 seconds. So that's fast. And if we do 2 plus 2.3 plus 1, it's taking 0.06 seconds. It's taking just about the same amount of time. What might happen is that when we are doing science and solving more complex systems, we are maybe going to be doing this operation not 1,000 times, but 10,000 times, or 100,000 times, or 10 to the 9 times. And if you do something 1 billion times, and the difference between two operations is like 1/10 of a second, you are going to pay a huge penalty cost in the end. And one of the issues that often pops up when you are trying to work with numerical values is using numerical values of different types. So if you have things that have floating point and things that have integer, every time you put them together, there is going to be a promotion that's going to be taking this value, putting it at a new place in the memory of the computer, and so on and so forth. So it is very important to be thinking about the types. We're going to see in 2 weeks exactly how much we can quantify the difference in performance between properly typed and improperly typed expressions and variables, but that is something that is important. The type system in Julia has a lot of other uses. We're going to be talking about dispatch next week, and we're going to be talking about how we can specialize some methods to do things depending on the type of the value. So it's also a tool for efficient programming and for expressive programming. It's not something that's here to cause performance issues, but it's something that you should be keeping in mind because that can create some performance issues. One thing that you can also do with a type system is do a little bit of check of your program. So let's use a very simple example. Say we have 1 and then we add 2. The result should be 3. That makes sense. But the result should not just be 3, it should be 3 that is also of a specific type, because we know we are adding things together and we're adding things of the same type, and they are integer 64. And so we could use this double colon notation to say, tell me if the result of this expression is not of the correct type. So let's say 1 plus 2 should be of the type integer 64. Everything goes well because we have added 1 plus 2, which are both integer 64, and so the result is of the same type. Now say we do 1.0 plus 2.0, and we are expecting an integer. And that can happen in more complex workflow. Let's say you have something that calculates the median values of integer values. You expect that the median is also going to be an integer. And so you might want to check that the output of the function is going to be an integer, right? And so let's say we are going to do a quick simulation here. And so if we say 1 plus 0 plus 2.0, is it an integer 64? We are going to have an error, and it's a type error. And it's because we are trying to do a type assert. So we are asserting the fact that the result is of a certain type. We expected an integer 64 because this is what we asked here. But instead, we got a floating point value. And that is a problem because it means that we have either thought about the type that we should get and got it wrong, or we have made a mistake in our programming at some place. And that is also the beauty of the type system is that you can use it to protect you and your users and your science against some of these issues. As a rule, during this class, every time we try something and we get this bold red message that says wrong, we're going to be very happy. It is the best thing that can happen. Because a lot of times the alternative is that we don't catch the mistake that we're making, and as a result, we get a result that is wrong. So we want the program to tell us that something is not going well. It's better to have a bug that we can fix than a bug that we don't catch and that is going to lead to wrong science. And so we are going to be spending some time dissecting these error messages and trying to understand what they mean, trying to understand how we can generate them ourselves. And it's better to have something that doesn't work and that we fix than something that looks like it worked because it gives a result, but the result actually doesn't make sense. So when you're doing something and you're building something, whenever you see a big red error message, that's good. It means that you have discovered something new to fix in your program. And that is what we are here for. There is another information that is very important about type, and is that the type system has what is called a hierarchy. So there is an organization of different types. Let me show you what I mean by that. So if we take the type of 2.6, it is a floating point number. And we can check that the type of 2.6 belongs to or is a subtype of number. So this little operator here, which is the inferior sign column, is called the subtype operator. So in Julia, as a rule, whenever you see something that has a symbol and a column or a symbol or two columns, it's going to be about the types, because the type system is very, very fundamental to how the language works. And we're going to see how we can use that to gain some new superpowers next week. But so what is this, the type? The subtype operator is going to return true if and only if all the value of the type on the left are also of the type on the right. So we can check that 2.6 is a number. We can also check that it belongs to the abstract float family. It is a number that has decimals. It is not an integer. And we can check that the type of 2 is an integer. It is a number that has no decimals. And it is also a number. Here is a neat little trick. It is also a subtype of any. So any is, or you say in computer language, I have no idea what the type is going to be. I can be literally anything. Any type that exists in Julia is going to work here. That should not be something we use fairly often, but just to show you that at the very top of the hierarchy of type is this thing called any, which is everything is belongs to any. So one of the first things we've discussed at the very beginning of this module is that the everything in Julia has a type. And we've done this thing, which was what is the type of the cos function. And the type of cos is a type of cos, and that is a neat little tautology, but it's not very useful. But we can check that the type of cos is actually a subtype of function. And so if you want to know the family, sort of, to which cos belong, then it belongs to the function. Let's say that you write a function, and this function is going to randomly return either a sine or cos. But you want the output to be a function. Then we could be using the subtype operator to check that it is actually going to be a function. There are some reasons for which cos and sine and other functions like that have their own specific type. We might end up discussing next week, or maybe not. That depends if we feel like going into the details of type systems and how they work. But they all belong to the super type, the super family of function. It's like, think of it as biologists, we can think of it as sort of phylogeny of types, where the common ancestor of everything is any, and then the further down we move, the more concrete types we have. And we can have types that are called unions, types that are called abstracts. There's a lot of things. It's all documented in the Julia manual, but that's the type that we actually use in 64, in 32, float 32, float 8. I don't know if there's float 8, float 64, whatever. And they all belong to different families. And we can adjust the behavior of the function that we write according to the type of these values. Just as a bit of warning, a bit of a side note to keep in mind for next week, I have been using the word function very, very liberally, in the sense of something that takes arguments and does something and give you a result or not. Next week, we are going to be introducing a very important distinction between a function and a method. And function can have different methods, but if you want to take some advance on the class material and you want to go and read the Julia manual, you will see that a function and a method are related but different concepts. I'm not going to explain why, because that is going to be the entire point of a module from next week. There are two things that we can do with type, two additional things that we can do with types that I'm not going to be mentioning today because I want to introduce some other concepts before, but I'm just going to give you a little bit of a spoiler. The first is that we can explicitly give a type to a variable, which is very, very important. So we can say population size in our model should always be a number of individuals, so it should always be an integer value. And that is going to be interpreted as, if I take my population size and I try to put a value that is not an integer, I will get the program will fail. So that is a thing that we can do. We can also annotate the type of the variables. A second thing we can do that is something that we're going to be experimenting with a little bit next week, is we can create our own type. So if we want to express a concept in biology, let's say we want to express what a population is. And a population, it can have the name of the species, it can have the population size, and it can have the protection status, whatever. Fairly usual biological information about the population of animals or plants or whatever. That is something that we can represent as a type that we create ourselves. So next week, we will have a quick introduction to the way we can define our own types to do some very specific analysis. So we are just scratching the surface of what is doable with the type system, but I want you to keep three information in mind. The first is we are going to be manipulating values. A lot of time we're going to be referring to these values using the names, and the name of a value is what we call a variable. The variables don't have types, it's a value. The value do have a type, and there are mechanisms that allow us to enforce the type of an operation, mechanisms that allow us to check the type of something that is returned by an operation, and every time we need to take something and convert it into another type, that is some extra instruction that the CPU, the computer, needs to perform before it gives us the result. So thinking about the type is going to be very important if we want to write programs that are fast. It's not necessarily the main bottleneck. I'm not saying that if you understand the type system, you are going to write models that are super snappy and will get done in like half a second. That's not what I'm saying. But if you do not understand the type system, you're going to be running into some common optimization pitfalls because of that. And so it makes sense to think about the way to express, especially numbers, and pay attention to the fact that 1 plus 2 and 1 plus 2.0 are not the same thing, and one is slightly more costly. In our daily lives during this class, it's not going to matter a great deal. If I'm being perfectly honest, we could do away with this entire module, and I'm only saying that because it's done now. But it's not something that is going to be important for the sort of model that we will write. And the scope of the project that you will do during this class, you could definitely get away with not caring very much about the type of the numerical values that you are manipulating. But if you want to do things that are a little bit more intensive, and maybe at the end of the class, if we talk about approximate Bayesian computation, if we do talk about neural networks and these things, it's going to be very important. So the more data we have to manipulate, the more operation we do, and the more operation we do on large volumes of data, then the more important thinking about the type is going to become. There's a lot of reasons for that. I'm going to introduce most of them over the next months or so. But just keep this in mind. It's not just a value, it's a value that has a type. If you understand the type and if you can reason about the type, you are on your way to not losing too much time performing conversion that are not necessary. So that was the short version of the type system and what is the difference between a value and a variable. It is 9:55. It's 9:50. So let's say that at 5 past 10, in about 10 minutes, we start again. The next module is going to be about another core fundamental principle, which is called iteration. We're going to understand how we can move across collections of things, and we're going to use a very common biological model as an example for that. So I will see you in 10 minutes, 5 past 10.